In this video we're going to look at section 3, which is rotational dynamics. Newton's second law for rotating objects can be written as follows. So net torque is moment of inertia. Remember, moment of inertia is the resistance to something turning or spinning around. So we're going to take that value and multiply it by the angular acceleration. So we get tau net, or the net torque, this capital I is moment of inertia, times angular acceleration. Okay, so, and it's written down here as well, and here is our translational formula. Remember, force was mass times acceleration. Alright, so here's some of the equations, and you're going to end up using these on the homework assignment for tonight. So here's what we just looked at. Tau net, or the total torque, is moment of inertia times angular acceleration. Well, this value, this moment of inertia, is mass times lever arm. This is squared, not times 2. That should be squared. Didn't import correctly here. So what that means is things get harder to rotate if the mass gets bigger, or if the distance from the lever gets smaller. Okay, and angular acceleration is acceleration divided by the lever arm, or the length of the lever arm. And here are all of our variables and what they solve to be. But by knowing these two equations, I can solve this into another equation for torque, which is torque equals mass times the length of the lever arm times acceleration. Now this is the linear acceleration, okay, not the angular. So if we take a look, a catapult propels a 0.150 kilogram stone into the air. Assume that the length of the catapult arm is 0.35 meters, and at that its moment of inertia is negligible, which means we're not even going to factor it in. So we're going to be able to use that new equation. If the stone leaves the catapult with an acceleration of 1.00 times 10 to the second, okay, again that didn't superscript, meters per second squared, what is the torque exerted on the stone? Well, we just look at, remember our equation, mass times the lever arm times acceleration. So 0.15 kilograms times our lever arm, 0.350, times 1 times 10 to the second meters per second squared. Here, I just plug those values in. And we get 5.25 Newton meters. And our units are Newton meters because remember, kilogram times meters per second squared is a Newton, and here is that meter. Angular momentum now. We've talked about momentum linear, okay? And remember, momentum was mass times speed. Okay, the higher the mass and the greater the speed, the more momentum it had. Well, it's similar in angular momentum. I is our moment of inertia, or how much resistance to change there is, times angular speed gives us this capital L, which is angular momentum. Angular momentum can be conserved, just like linear momentum is conserved when we don't talk about forces acting against it, like air resistance and friction with the road if we're talking about a car. Angular momentum is conserved as well. So when the net external torque acting on an object is 0, so there's no torque acting on it, the angular momentum of the object doesn't change. Okay, it's not going to accelerate, it's not going to decelerate. It's going to stay right where it is. So this is the law of conservation of angular momentum. Remember, moment of inertia decreases as the mass nears the center of the object. We talked about the bowling ball yesterday and the hollow ball, and how the one with the full sphere would roll down the track quicker because its mass is closer to the center. Well, this is also true for angular momentum. And figure 811 in your textbook shows a figure skater. And if any of you guys have watched the Olympics or any figure skating, when skaters skate and they jump into the air, when they twist, they're going to pull their arms and their legs closer to their axis of rotation. This allows them to spin faster and longer and get more spins into one jump because they're conserving their angular momentum by keeping it in. They're lowering their moment of inertia. Okay, they're decreasing that moment of inertia. They're making it easier for their body to spin around. Rotating objects also have kinetic energy. Remember, kinetic energy is energy of motion. So as something is spinning around, it has kinetic energy. In this case, we call it rotational kinetic energy. And it's expressed here. Kinetic energy of rotation is 1/2 moment of inertia times angular speed, and this should be squared, not times 2. And mechanical energy is conserved. Remember, mechanical energy is all of our energies, whether it's translational, rotational, or potential gravitational energy. All of these added together would give us our total mechanical energy. And here, the second line here just gives us those values with the equations rather than the expressions above it. So mechanical energy is conserved. Initial mechanical energy is going to equal the final kinetic or mechanical. So if we have a solid ball with a mass of 3.25 kilograms and a radius of 0.75 meters, starts from rest at a height of 2 meters, rolls down a 30.0 degree slope. This is figure 8.15 in your book. What is the translational speed of the ball when it leaves the incline? Now, yesterday I showed you a picture. It had all the different equations for the different shaped objects. Well, using that information, and it's outlined in your book, we find that the final velocity squared equals 10/7 times acceleration due to gravity times the height. Okay, and the book goes step by step on how they come up with this equation. I want you to know the equation and know how to use it. So, for this, we're going to plug values in. So my final velocity squared is 10/7 times 9.81 meters per second squared. Now remember, I'm using positive because the negative just shows direction, and we know it's going to go in the negative direction. Plus, when I go to take the square root, if I have a negative answer, it's not going to like it. We don't want I in our answer. 2.00 meters is our height. So now, when I calculate this out, my final velocity squared, if I do my 10/7 times 9.81 meters per second squared times 2 meters for our height, we get about 28 meters squared over second squared. Well, when we take the square root of it, we get 5.29 instead of meters squared second squared. When we took the square root, it's meters per second. Now I want you to think about this problem and what would happen if our ball was 4 kilograms instead of 3.25. If we look at the equation, mass doesn't factor in at all. Its final velocity is going to be the same. What changes, though, is the acceleration. It may get to that final velocity quicker. And this slide just shows the equations for this section. You should have this handout along with the homework. Let's have that homework sheet due for tomorrow. Have that ready when you come to class tomorrow.